We will continue working it through Unit 3.5 today, more specifically, going over some problems where motion is in more than one direction. When we have motion in more than one direction happening, such as on a ramp, we have to be careful about what we say our normal force is equal to. Because the normal force is not, because it's perpendicular to the surface, it is not going to be equal to the weight as it is when the object is laying flat on a surface. However, we are able to do some things. If the object is at rest, we can kind of work with it, and it's not too bad. Look at that color, that looks nice. When the object is at rest, there would be no motion. Frictional force would still be there, opposing the motion. Because when we look at this, we might look at this problem going, well, I don't see, if it's not moving, where's the equal there? It's there, we just haven't taken it into account yet. What we need to do is to look at, what is the opposing force of that normal force? Well, that becomes force of gravity in the y. I'll change the color here. That is force of gravity in the x. By all technicalities, if I would have drawn a really good triangle there, that should be a right triangle. So what is the thing that friction is opposing? It's opposing gravity in the x direction. The thing that's going to want to pull it down to the surface. Why is the normal force not going to be equal to the weight? Is because at a certain angle, it's decreased some. It will be increased as we lay it flat. A trained sea lion slides with a constant acceleration down a 3-meter long ramp into a pool. The ramp is at an angle of 23 degrees above the horizontal, and the mu sub k is 0.26. 0.26. How long does it take for the sea lion to make a splash? So let's resize this here. We're gonna need some room. And as always, when in doubt, draw it out. So I'm going to try to get a slightly reasonable 23 degree angle on this, but it may or may not work awesome. We're using my protractor. So 23, just to kind of draw it out correctly. All right.
Are we calculating when it touches the water or when the actual splash takes place? The splash
within reason. We're not gonna get it down to probably the 100th of a second. We're just gonna kind of go with. Right, so we'll have our ramp here. Roughly 23 degrees. Let's give the water right. So, because my artistic abilities are probably a little lacking, let's go. Gray line is just a box. Let's see, sea lion. We're just gonna. They might be brown, but I'm gonna use a gray box there, just because. Right? Things we know. Always important. We know that there's going to be frictional force that way. We know that there's going to be a weight straight down. Weight is always straight down. Okay. We will also know weight works friction. This force of gravity in the y direction. Force of gravity in the x direction. And there would be our normal force perpendicular. We know that it's sliding with a distance of 3 meters. We should also probably write out that the mu sub k is equal to 0.26 distance, and we'll say in the x direction. And the reason why we can say that is if I needed to look at this, rotating it so that it looks like it's in one plane would make our lives easier, right? That's sometimes what it's not a bad idea, that if we had to, taking this and then rotating it, because now all of a sudden, now it looks like a problem. You're like, I've seen a problem like that. Because we can get rid of some things. If I get rid of some of these parts, we can kind of see force of friction. Gravity in the x is going to be your direction in the x. Your normal force, just perpendicular to the surface, just like it would be on a flat surface. Force of gravity in the y is your opposite. The thing that doesn't make a lot of sense is that where does that weight come into play then? But that gives us the other two parts. Okay? So sometimes it might be easier to kind of look at it and, okay, how does this look? And literally rotating your paper might help on how that works. Okay. Not only that, drawings get to be very messy real fast. Would you agree? And therefore, sometimes you're like, okay, I need to redraw this and get rid of some of the other stuff that's going on. That was a little too large of a weight there, maybe. And kind of cleans it up a little bit, and then we don't see the ramp that it's on. It's there, it's important, but we're more worried about what's going on with this sea lion and how fast it's going down. It's going to have a constant acceleration, and so we're going to have to start looking at some equations that we have. Okay? We'll also need to pay attention to our vectors, because the opposite of the angle, so it'll be the sine of 23 is going to be equal to the weight. No, opposite is be the force of gravity in the y. Force of gravity in the x divided by the weight. Opposite over hypotenuse. Then the cosine 23 is going to be equal to, I got to put those two close. The cosine force of gravity in the y divided by weight. Because we don't have a weight, or we don't have a mass, so we're going to have to factor it out with this as well. We're also going to know that there's frictional force, and that the frictional force is going to be equal to mu sub k times the normal force, which we also know that the normal force is going to be equal to the opposite of the force of gravity in the y direction. So we have to factor that out. And we know that the F net, right? The net force is the sum of all the forces put together. And in this case, that becomes the force of gravity in the x minus the force of friction. Because force of friction is going to oppose it sliding down the ramp. Okay? So we start kind of manipulating our equations to algebraically substitute some things. Right? We know that we need that frictional force is that, but we're also going to have want to get rid of some things here. So we can say that the frictional force is equal to mu sub k times the opposite of the force of gravity in the y, doing the substitution for n. I then can algebraically manipulate multiplying both sides by W for both of these equations to also give me weight times the sine 23 is equal to the force of gravity in the x, and weight times the cosine 23 is equal to force of gravity in the y. We can then start adding equations such as this. Start getting rid of some things, because the force of gravity is going to be that one's going to be there. But F net is also equal to mass times acceleration, which is equal to the force of gravity in the x, which is equal to the weight times the sine 23 minus, that was frictional force, my bad. Nope, that was right. And then force of gravity in the y minus the mu sub k times weight times the cosine 23. Running out of room real fast here. And there should be a negative of that as well. So looking at my signs, since that's a negative there, when I substitute in, that whole thing needs to be by negative, so that would be there. Weight is what? Weight is equal to mass times gravity. Okay, and so we can go, we could factor out a weight, but we're going to still have gravity. Well, let's just factor out weight. So let's go weight times sine 23 minus mu sub k minus the cosine 23. If I distributed that, it should be somewhat strong. It should be right. Therefore, then I only have to rewrite that once, and then mass times gravity times the sine of 23 minus mu sub k times the negative cosine of 23 is equal to mass times acceleration. Divide both sides by mass to get rid of it. Therefore, our acceleration is going to be equal to gravity times the sine 23 minus mu sub k minus the cosine of 23. There, we'll want to say what, and then solve for a to find time, giving us a distance. What was that equation that we could use for that one? Now, the acceleration is the equivalent of we'll have to do some, some equations that we'll use, but I'm going to algebraically manipulate this. Distance is equal to v sub I times t plus the 1/2 at squared. Because the initial velocity, we can go under the impression that it was 0. I ran out of room, so it's up in the corner. So because that's 0, you would get rid of, right? I then have to manipulate things, right? And if I do the manipulation correctly. Okay, so we have two options. We can set everything to A and then solve for t right off the bat, or we can do the long equation here that it would be A is equal to gravity, which would be 9.81 times the sine of 23 minus mu sub k, which is 0.26 times a negative cosine 23 to give me an acceleration of an acceleration 4.08. No, so 0.02. Degrees. Okay, so now I can take that. That's my meters per second squared. I know that it was 3 meters long. Is equal to 1/2 4.07 t squared. Solve for that. We can multiply it by 0.5 right off the bat. If we wanted to get rid of it, we would have 3 divided by 2.04 roughly. To give me about 1.47. Take the square root of that. Go 2. Go 2. We end up with a time of 1.2 seconds.